Ma'am, we'll just start in 5 minutes.
Okay, no issue.
Ma'am, we'll start now. Am I audible? Ma'am, we'll be starting now.
Hello. Yeah, can you hear me? Yeah,
Yes, ma'am. All
yeah.
right. Good
Sure.
evening, ladies and gentlemen. I, Arnavjeet Verma, extend a warm welcome to all of you on behalf of BITS Embryo. We are delighted to have you here for tonight's enlightening talk titled Myth to Math Impact and Applications of Quantum Technology. Quantum computing, a rapidly evolving field, uses the laws of quantum mechanics to tackle complex problems, merging aspects of computer science, physics, and mathematics. A technology that was once the stuff of science fiction has made its way to being applied in our daily lives. Quantum computing has the potential to revolutionize fields all across STEM, from communication to climate research to financial analysis. Today, we'll try to cover some of those bases and understand directly how quantum computing affects our progress as a society. To delve into the same, we have with us a distinguished speaker today, Dr. Aditi Sende. Her groundbreaking work in quantum computation has earned her prestigious accolades. She is the first female physicist to receive the coveted Shati Swarup Bhatnagar Prize. She is also the member of the Indian Academy of Sciences. We are privileged to have her here with us to gain insights into this fascinating world and its impacts on our daily lives. Over to you, ma'am.
Yeah, thank you. Thank you very much for the invitation. It's always, actually, I think it's kind of my, I don't remember, maybe third or fourth kind of talk or hear me?
Yeah,
Yeah, okay. So, so thank you very much.
all right, ma'am. So, first question is, can you describe your academic journey and how you decided that quantum computation is the field for you?
That's okay. So, first of all, uh, as you said, that this subject is quite interdisciplinary. So, actually, I am not a physics student. I mean, training by training. I did my bachelor in mathematics, which is a major, and physics chemistry as minor. Then I did MSc in applied mathematics, which is previously, I mean, long back it was called mixed mathematics. And also probably two renowned scientists whom you know, Satyendranath Bose, whose name for this boson, as you know, and Meghnad Saha. They both are actually the alumni of mixed mathematics from University of Calcutta University. And I also did kind of applied mathematics, and my major, I mean, among this many subject, I have specializations on quantum mechanics. So in that sense, I was interested to learn quantum mechanics, quantum physics. I mean, I am still doing that, but that's a starting point. And then it's around the last century, and so almost at the end of the last century. And so around 2000 or 98, 99, as you know, the after the initial kind of theoretical results or theoretical, I mean, breakthroughs. There are experiments which were kind of trying to realize all the theoretical results around 2000. Okay. And in India during that time, some of us, I mean, some students, mainly PhD students and some postdoc, who were interested in quantum physics, foundations of quantum mechanics, we got somehow interested in this subject. And we started learning ourselves. And then I went abroad for my PhD. And so, I mean, I started liking, I started reading, and I get interested. So, in this way, I started doing this quantum computation.
Right, ma'am. And so, quantum computers work on two main principles, entanglement and superposition. Could you break these down for us?
Yeah, first of all, the statement is not quite correct. Okay, so first of all, it is not known as yet whether entanglement at all will play an important role in quantum computation. It's an still an question which was so. Entanglement is useful for many quantum protocols, specifically in quantum communication. So, if we really want to have a higher efficient quantum communication protocol, which will be better than the classical ones, then we know that for sure we require entanglement. On the other hand, in case of quantum computation, so all the known algorithms that we know, which actually give you faster or give you a higher speed up than the classically known algorithm, there we know that in some point, so you have several steps to execute certain problem, and in the middle or in some states you may require entanglement, but overall the efficiency, whether the efficiency is really connected to entanglement, it's not yet clear. Although recently there were, not recently, but there are some another quantum computation protocol which are known as measurement based quantum computation protocol. There we know that the entanglement is essential. So what I want to say, the question that you ask is not I mean scientifically I should say, is not yet known. So what is the main ingredient that gives us power of quantum computing or better efficiency in quantum computing, that is not clear. And surely it's not entanglement, this is also not clear. Although, as you correctly pointed out, the superposition is one of the important ingredient. So uh, first of all, the superposition is something, can I show some slide if possible, or
Yes, ma'am. Yes, ma'am.
yeah, okay. So just allow to share screen maybe. Um,
Would already be there.
can I share now, or you have to allow something?
Yes, ma'am. You
Yeah.
can share.
Okay. Yeah. Okay. So I just prepared something I had actually. So in case of superposition, just to tell you what is superposition, as you mentioned, can you see the slide, right?
Yes, ma'am.
Yeah. So classically, we know that we can have a live cat or date cat, right? I mean, we see that. And so that can be mapped like it's a tossing of a coin. So alive can be mapped like a head, and the date can be mapped like tail. Okay. So, or in classical computer language, you can think that one of them, alive, can be mapped as zero, and tail can be mapped as one. Okay. So if I really want to do a classical computing, hello, can you hear me?
Yes, ma'am.
Yeah. So if I want to do classical computing, then my the data or anything which I encode in bits, that is one of the zeros or one. Okay. I wrote it like a bracket notations, which is in quantum mechanics. You can say that's head I map, or I denote it as zero, and this is tail as one. Quantum mechanics tells us that there exists also a state which is a superposition of alive plus dead cat. That means instead of only head and tail, there exists also a state which is some kind of zero plus one. So this is called a act, not only 0 plus 1, but any arbitrary coefficient alpha 0 plus beta 1, where alpha beta are arbitrary complex numbers. So there are some constraint which is something normalizations, but let not discuss that. And the 0 1 in a quantum language can be encoded. For example, the if you think about a spin degrees of freedom, then 0 can be up spin, 1 can be down spin. If I talk about a polarization experiment that we people do in photons, with photons, then the uh, right circular polarizations can be mapped as 0, left circular can be mapped as 1. So this is the arbitrary quantum state, and this is quantum mechanical postulates tells us that along with alive and dead cat, we can also have an arbitrary superposition of alive and dead cat. And so this is a superposition principle, and you are absolutely right in a sense that this is the one of the main ingredient that gives the power in quantum computation or quantum algorithms. Okay. And so the in case of quantum mechanics, you can think that if you have any situations I want to describe in a physical system, that can be mapped in a vectors in a linear space with an angle defined, which is called Hilbert space. Now, in case of if I want to describe two quantum mechanical physical system, then I have to take a tensor product of the Hilbert space. So tensor product of the linear vector space with an angle defined, and with based on that, I can define something called entanglement. So if there are two parties, then one of them prepares some state phi A, another prepares some state phi B. This is called the unentangled state. So to prepare an unentangled state, Alice and Bob particles should not interact. They can prepare this unentangled state even when they are situated in far apart location, and they can be also called useless states because they are not useful for any quantum mechanical quantum protocol, none of not in quantum communication or quantum computation, and mathematically they look like that. So you can think that you prepare 0 at Alice's side and 1 at Bob's side, or 0 at Alice's side, 0 at Bob's side, and so on. So on the other hand, to prepare entangled states, two quantum mechanical systems should interact, and so to prepare entangled state, Alice and Bob will not be able to prepare these states when they are situated in too far apart locations. Say, for example, Alice is situated in Allahabad and Bob is in Pilani, for example. Then just in our laboratory, we cannot prepare in our own laboratory doing something, we cannot prepare entangled state. So there should be some source. Say, for example, source is in Delhi, for example, and source suppose prepares the entangled state and send one particle to Alice, another to Bob, and then Alice and Bob can share an entangled state. Now, mathematically, this cannot be written in this way. So, a state is said to be entangled, phi AB, which I denote, when it cannot be written like phi A tensor phi B. And as I said, that to prepare this phi AB, there should be a source where two quantum mechanical particles should interact, and then then we can prepare an entangled state. Now, most of the protocol that we know, there we, for example, in quantum communication, as I said, entangled states are useful. And in quantum computation, in some of the protocols, we know that in certain steps we require entangled state, but not yet proven that entangled states are the main ingredient for the higher efficiency in quantum protocol. So this is the scenario. I hope this is clear. If you have any questions, you can ask more.
Thank you for that insight, ma'am. Ma'am, we have seen some of the current quantum computers that exist. For example, IBM has, and we have
Yeah,
seen that they are mostly kept at very low temperatures, very close to absolute
exactly.
zero. So why is that crucial?
Yeah, actually, this is crucial because, as I already said, if we have so the entangled states or the superposed states, if we want to keep those states, because they are the main ingredients for the higher efficiency. Now, to keep them, so if the superposition state becomes only the state like 0 and 1, like a head and tail, they actually represent kind of classical state. Okay, so they are not useful, as I have said. So now if the temperature increases, that means somehow the noise is increasing into the system, and then the quantum property that are required for higher efficiency, you will be losing those property. And so if we really want to use say anything like superposition state or the entangled states, we have to minimize noise or decoherence, which you call, so that the quantum features that are required to obtain higher efficiency, they remain as it is. So this is that's why you require very low temperature, so the decoherence can be decreased, because when the temperature increases, in some sense thermal noise are increasing into the system, and typically the states lose their quantum property. But here one should also remember that all these experiment that you have talked about the superconducting, where this IBM and the Google, they're all reporting. And so there you require low temperature. There are physical systems, for example, the photonic one, where you can also do linear optics, quantum computing, or quantum communication experiment that also reported some years back, where people did quantum cryptography through satellite and so on. There you don't require any kind of this low temperature, because they did experiment, for example, through satellite. They prepare entangled state in satellite, then send two particles in two cities. Okay, and of course that means they cannot, from satellites the photons are coming. You cannot think to make them in zero temperature. So in that experiment is clear they can keep quantum properties even when the photons are traveling through environment just like normal. So, and also there are experiments between two cities where photons are traveling in free space, through optical fiber and so on. There you don't need to really the low temperature. Okay.
So, with the absolute basics covered, we will now move on to the practical impact of this technology. It is really important in today's scenario that any new technologies that we develop help in the progress of mankind, especially through the United Nations Sustainable Development Goals. And quantum mechanics can help us make more energy efficient systems, as you mentioned. So could you shed some light on that with some reference to your work on quantum batteries?
Yeah, okay. So that's actually, I mean, kind of, there are some kind of effort to show that, if you use quantum mechanical systems to store energy, and so what we understand from battery, the normal battery that we use, for example, our laptop is running or our mobile phone, that means there are some kind of chemical energy which are transferring to electrical energy, and whenever we require we can kind of extract energy, right? And the similar thing we want to build in by using quantum mechanical systems, as I have already mentioned that the interactions are necessary, for example, to prepare entangled state. So some states which has some quantum properties which we cannot mimic by a classical mechanical systems, okay, like two balls or something when we describe classical mechanical way. Okay, so the point is that it can be shown. I mean, for example, the work that you were saying about our recent work, where we show that actually, if we have to quantum mechanical system, when they interact, you can store more energy, and you can also extract more energy compared to the system when two quantum mechanical systems are not interacting. Okay, this is first point. Second point is that, as I have said, that it's also important that the battery or whatever quantum technology you build, they're robust against decoherence. And what do you mean by that? Because they should keep their property as much as possible, as much quantum properties they should keep, so that we can use that for certain building certain quantum technologies. Okay, so we show that if you can build quantum batteries, that they can be robust against decoherence as well. But here I should also mention these there are also work on quantum refrigerators, quantum transistors, and so on. Okay, for example, in at HRI in our group we are working on that subject. These also help us, apart from quantum technology development, it also help us to understand quantum thermodynamics. So I think that many of you here have learned thermodynamics, classical thermodynamics in your
Yes.
coursework. So the point is, when you go to a microscopic particles like atoms or molecules or the small particles, we still don't know what will be the thermodynamical, like second law, like other laws that you have learned in your coursework, whether they still remain valid or not in a microscopic regime. Okay, so by kind of designing these quantum technologies like batteries, refrigerators, we also try to understand whether quantum in the quantum domain, whether thermodynamical principles that we learn in for the classical system still remain same or not. So this is another important direction that also people. So this is kind of fundamental research that we are doing.
Right. Ma'am, you mentioned that quantum technology can also be used for communication protocols. So is a quantum internet the actual future? How does this play into maybe 6G communication, and what are some protocols that currently exist? What are some in development?
Yeah, so the internet is actually kind of, people are trying to build quantum network very, I mean, both theoretically and experimentally. There are a lot of work going on, including some of our work at HRI. In our group, we are kind of constantly working on that. But as I said, the main challenge or one of the challenges is the following, that to keep the, as I am kind of repeating my words, that's when we want to do quantum network or quantum internet, if we really want to beat the classical efficiency, we have to somehow generate or distribute or spread entangled state among many parties. Suppose the same internet, now we are doing this 38 people we are here. So suppose I want to do the same thing with the quantum internet. That means somehow we have to have a kind of entangled state between 38. Okay, suppose I am the sender and all are the receivers, so I have to be connected through entangled states with these 38 people. Now this is not an easy task because of decoherence. And so you can also imagine, I think now we can have a very stable internet, but few years back, even when we were talking over phone, we usually get disconnected
Yeah.
quite easily, that yeah, there is no connection, or there is some wrong connections. I don't know whether you people have faced. We were, when we were young, it was a very common that I am talking with someone, actually instead I'm talking with someone else, because there is some middle one there. So that means there is, the network has some issue, right? So this is the main trouble, that if I want to build an entangled state, we want to distribute among these 38 people before starting the, say, Google Meet, then they keeping this entangled state for a longer durations, even for a smaller duration, is hard. And another thing is that more the distance, there is a more possibility of the decoherence. And so keeping entangled state is difficult. And so although quantum internet can, people are thinking to be the future, and because of also the cryptography, etc. So the point is that it's still the people are doing the research, that how efficiently you can distribute entangled state, and then after distributing, how you can really perform the communication protocol. So these are kind of open questions, very, I mean, kind of very exciting research areas in this field.
So while researching for this, I came across a sentence like, just wanted a views on that, that nature is the best quantum computer we have, and a sunflower can perform calculations that even the current most powerful quantum computers cannot. So like, does nature really follow those quantum principles on a macro scale?
Good question. Actually, that we don't know, frankly speaking, because of course we say that everything can be described quantum mechanically. Okay. Only thing is that suppose I want to describe even a sunflower by quantum mechanical laws. That means all the atoms, molecules, and everything has to be of the sunflower has to be described quantum mechanically. So it's a very highly nonlinear many body system. But whatever we see about the sunflower, whatever if air is flowing, the flower is moving, right? We see that all the time. So, and you can see from its movement that which directions air is flowing, right? So, these kind of thing you can well describe by classical mechanics. So, there is no need to go to quantum mechanical, because as you know, if I have a many body system, it's very hard to get the solution of this problem, that in which directions it will move and so on. But in principle, it is possible, but we don't require that. We require, we can, classical mechanical systems can, or the classical laws that we learn from Newtonian mechanics maybe are more sophisticated, the Hamiltonian or Lagrangian. We can solve certain problem, and that problem can well describe that why sunflower is moving like that, which direction it should move when the wind is flowing, say, in northeast and so on. So there is no need. Now, the another question is, you can ask that suppose I am able to solve it, okay, this I write down the sunflowers Hamiltonian and everything. I write down in Tapa many body system. Now the question is whether this will finally tell the law that I get from quantum mechanical laws, or the if I solve these equations of motion, can I get back to the Lagrangian equation of motion from where I get the solution? So this microscopic to macroscopic, this kind of transition is still not known. I mean, this is a quite interesting question, but we don't know. At least I don't know.
Ma'am, so I'll come to some common applications that are going on right now. So the simulations that are being made on quantum computers, could you talk about how those affect research in medicine, maybe climate change?
This is actually very recent development. So people still don't know. There are some kind of initial results coming up that because the this area, this pharmaceuticals or the medicine, this kind of thing. So what we understand from the original Feynman question, that of course if we have a quantum computer, we will be efficiently simulate or find out the energies or eigenvectors of the Hamiltonian that is under consideration. So some problems that we cannot solve in a classical computer, we expect that we will be able to solve in a quantum computer. That is still true, but we don't know what will be, the whether that will be helpful in the medicine or medical research. That we still not clear.
So as you said that we are currently researching about many aspects of this technology and it is not sure yet. So are there any concerns that quantum computing will maybe get stuck due to physical or technological limitations before it can be scaled up for general use?
Yeah, I think that's what people are trying, because there are certain kind of 400, 300 qubits, 100. So around hundreds qubit, I should say, people can build. Okay, so but if we really want to get a quantum supremacy as such, to show really that the quantum computer is more powerful than the classical, we need thousands of qubits. So the state that I have shown, kind of superposition state, alpha 0 plus beta 1. So these kind of states we require to build quantum computer of thousands. Now this is still people are not sure that how to build, how to really scale. Now again, I mean, scale, you can build, but the point is how long you can keep its quantum features so that you can perform all the manipulation, which we do in case of laptop. It's not that we build a laptop immediately, we throw away. We use it for 3 4 years. So similarly, to have the quantum computer, how long we can keep its quantum features is the challenge.
Right, ma'am. So you mentioned that we need thousands of qubits, and currently the challenge is to really maintain those quantum properties at room temperature, despite all the decoherence. Are there any other drawbacks of this technology that delay the research and the scaling up of this for general use?
Yeah, I think that probably the one of the main challenge is decoherence, and of course, after we can beat, there is always a possibility that classical computer also has faced. So there is something. Suppose I built initially the classical computer, which were quite efficient, was huge, right? Even I think 1970s or so on, when their computer was almost like a room size. Now it's kind of, you can have an iPad or even a smaller one, which are as efficient as many others. So the point is that after we build, there is of course a question which also requires time, the how to make it smaller in size and compact and so on. So that's a different challenges. But I think the main now challenge is to really build some 1,000 qubits quantum computer, and to really show that you can keep that or the quantum features as it is for some time, because still we are not sure about quantum memory, where the quantum systems can be kept. Like here we have initially DVD, CD, memory stick, etc. So, and also the error correction has to be performed. So we require all this. And so these are kind of, I think, current research areas that people are putting a lot of efforts, both theoretically and experimentally.
So this is, I guess, similar to the silicon race that happened a couple of decades ago when research in that was booming. And
Yeah.
I think there is no denying that as India, we kind of got lost in that race. The West took up, China took up for manufacture of the chips. So can we learn anything from that to become leaders in some aspect of quantum technology in the future?
Yeah, one important, it's true that all this quantum communication that I have talked about, around 1,000 kilometers, the satellite based quantum communication that was reported by China. There are a lot of quantum computing also, which was, for example, 2019, where quantum supremacy was shown by Google. Later on, in Chinese group, they show that there is some issue that you can solve it very quickly, and so on. So they are really as per the West, I should say. In India, people are trying. There are some initiative by Department of Science and Technology. There is now also an initiative by government. But the point is that in quantum computing, I also feel that apart from there are several races, because one thing is of course the quantum computer, which is the main goal, but also there are small quantum technologies that, like what we discussed about quantum batteries and other small technologies, quantum metrology and other things, quantum sensors related to metrology and so on. So there are other technologies which we can still be in a in we can still, I mean, there are many areas or many directions which still are unexplored worldwide. uh, so there is a possibility that we may expertise in one of the directions which people are not focusing. So there are many directions which are even not known, as you mentioned, in case of, for example, medicine and so on. This is a very new direction people are trying with machine learning and so on. So there are many directions that are coming up, which even a 5 years back people haven't thought about. So I think in that sense, and there is also fundamental questions like understanding quantum mechanics, understanding some other quantum mechanical properties, thermodynamics. There are many directions in which I think India can contribute. So, in that sense, if we are kind of properly, we can do the research in next few years, we will be in a good position.
And so you mentioned that there are some fundamental issues, fundamental questions in quantum mechanics that are still left there to answer, up along with some new technologies that are coming up seemingly every day now. So how can we make quantum research in India more maybe industry oriented rather than just an academic expedition so that the the product is more and it is actually more marketable, it generates more revenue. So from that point of view, maybe we can become leaders in that.
Yeah, that's actually going on, because I think there are many startup companies which also in India, I mean, not in abroad, of course there are many, but in India also in last few years I have seen several startup companies. We are trying to build something like random number generator, which is required for quantum cryptography. They are trying to build some parts of quantum computing which are also required for some circuits to build. So there are many parts which, as I said, there are one thing is that to build quantum computer, but there are also some parts or some things which you can also build in a compact way. So I think there are many startup companies coming up, which also are, so there are people who are getting job also in case of quantum research, this startup companies, and they are seriously thinking about expanding this, and I am hopeful that there will be something more.
Ma'am, so as you mentioned that the Department of Science and Technology is already supporting this research with the National Quantum Mission. Do you have any suggestions as to what more can maybe the government do? Maybe various universities around India, some startups can play a role in furthering research in this area.
Yeah, I mean, you are in a I mean, in our case, the point is that coordination is also requirement. I mean, academic and industrial collaboration is still missing. So,
Right.
in some sense, this can be increased a bit, and in this, I think that's you know, first of all, there are many developed countries. So we already have a research institute which are which are kind of only doing research on quantum technologies or quantum uh, both fundamental science or foundation aspects of quantum mechanics as well as the technological aspect, and they can have a much more planned way to interact with industry. On the other hand, we are still not really I mean, few years back we were kind of isolated doing research. Now it's much more organized due to this DST initiative, quantum enabled science and technology. I think they launched in 2019. We have regularly meeting where we meet other people and exchange ideas and so on, but still it's in academic area because all those research projects are given to academic people. Because initial of course initial thing is that first to understand how the the subject is moving, then you are planning to start with industry, and that is what probably slowly it's coming up. But maybe more research kind of industry and academic collaborations, we require much more organized way to handle things, that I feel.
Right. So, one question before we move on to the audience questions. How can we as undergraduates contribute to research in this new area? What paths can we follow? What fields we can explore?
Yeah, I mean, as I said, this is I mean, you also in the beginning you mentioned that this is a quite interdisciplinary
Yeah.
subject. So if we really want to develop both, I mean, kind of academic and industrial collaboration, I think that we require many kinds of students. So, for example, we need PhD students for doing the research. We also need technologically advanced people like engineers. I mean, engineers we require, I mean, heavily if we really want to build some good industry and so on. So I think that somehow, I mean, there can be internship in this small in these companies that they are starting up, where people can do to understand the how really things are working and so on. At the same time, people who are interested to do research, they can of course contact or do internship in the research institutes or the universities. I think in that way we will be able to kind of get the manpower, both kind of experts in one in the from the technological side, another in the academic side. So this is what I understand.
Yes, ma'am. Thank you for insights, ma'am. Ma'am, we'll move on to audience questions now. So anyone in the
Okay.
audience who has a question can raise their hand and you'll be allowed to ask. If anyone has a question, you can raise your hand. Satvik, you can go ahead.
My question to you is, what are the current obstacles in the quantum computing scenario that have stopped the quantum computers to 100 or 200 qubits? Why can't they push till 1000 or 2000 plus qubits?
Yeah, so any small computers that you build, usually like a classical computer, we really want to do. So if you have in a classical computer, you have some bits that actually comes as an input. Then you manipulate these bits by applying quantum gates or by applying gates, okay, in a classical computer. Now, in a quantum computer, you do similarly. The inputs are quantum states. Then you actually perform quantum gates to manipulate this initial state. Okay. So The point is that they try to first build this 100 or 200 qubit quantum computer, and to see that after, because there are several ways imperfection or decoherence act on the circuit. One is when you apply quantum gates, they are imperfect. They cannot be very, without accurately, they cannot be applied. And so they try to find out what are the gate fidelity that they are getting. And if they are very low, then there is no point of performing quantum gates or to achieve some task to fulfill. This is not possible. So even with 100 and 200 qubit, it's hard to, you know, uh, they are not able to get or they are not able to keep quantum features for a long, for some time. So that's why they cannot go beyond 200 or 400, even 1000 qubit. They cannot go because of decoherence that I have mentioned the whole time.
Thank you, ma'am.
Navya, you can go ahead.
Yeah. Good evening, ma'am. Ma'am,
Evening.
so what should the undergraduate, like, are there specific programs that are specific to maybe quantum information theory and quantum computing that the students can pursue in their undergraduate, basically
Yeah,
research?
yes, I think there are some this NPTL, or there are some coursework on quantum computing. There are also, I think, Qiskit also are doing some kind of thing. But I really feel that there are academic institutes, universities where one can apply for an internship, okay? And then they can learn, because in summer usually is free and winter also. So summer and winter one can do internship and can learn. And if someone is interested in the technological aspect, they can go to an experimental lab, or they can go to some industry to understand things. So this is the way I understand one can explore this subject.
Okay, ma'am. Thank you.
If anyone else has a question, they can raise their hand. All right. Before we wrap this up, we would be grateful if the audience could. Okay, there is a question on the chat
Yeah.
box.
So that's what he said. Okay. Quantum computing path, trapped and quantum dot photonic seems most promising. They're very difficult to tell. Actually, superconducting trapped ion are kind of ahead of many, but it's true that now photonic quantum computing is also promising. So people are still, one way to beat this 100 qubits obstacle, people are thinking that to build a hybrid quantum computing, which is, which can be trapped in and say, for example, and photonic. Okay. So there are many proposals. So in that way, it's not clear really which one is better than the other one. So of course, trapped and superconducting has some advantages which photonic doesn't. On the other hand, photonic has some advantages which trapped and or quantum or superconducting or quantum dot does not have. So it's not very clear that which one is really, which physical systems will be better to implement quantum computing. It's not clear.
Manula, I hope that answers your question. Before we end, I would just like to address that Professor Naveen Singh is also in the talk with us today. Professor Naveen Singh is a professor in the physics department. Thank you very much, sir, for joining for the talk. Now, before we wrap this up, we would be grateful if the audience could fill out the feedback form for this event. The link will be shared on the chat box, and the recording and synopsis will also be shared later on. Bits Embryo strives to organize more of these talks, and we hope we have a great response going ahead too. Thank you all for your time. Have a good evening ahead. Thank you so much, ma'am. Your insights were really helpful, and I hope that a lot of people are interested in quantum computing. Their horizons have been broadened by your talk. Thank you so much, ma'am.
Thank you. Thank you for inviting. Very nice talking
Our
with you.
pleasure, ma'am.
Yeah.
Thank you so
Thank,
much, ma'am.
yeah. Bye, everyone.